Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. All right. Okay. Just making sure that everything is good there. Okay. All right. Thank you for joining another session. We have two main activities today. Of course, we're going to be continuing with lecture, but there is something that I wanted us to do before that, as well as just some general PSAs, some announcements. Okay, so just a reminder, if you haven't done it yet, fill out the doodle poll for tomorrow's session. Right after class. So by like 8 p.m. tonight, I'll be finalizing the time and setting that up. Test 2, that's the only other testing thing besides the final that we have left. So test 2 is on Friday, December 4th, just a reminder there during regular class time, which is during recitation. The final exam is Monday, December 14th at 5:30 p.m. So keep checking the official final exam schedule because they are updating things. And as you guys may or may not know, a lot of schools have been closing down based on what's going on. So don't know what's going to happen in December or if anything has to be rescheduled. So keep checking. But as of this moment, that is the date of our final. So hopefully you can for now, pencil that in and plan on that being the date. So until further notice, those are two important dates. And of course, like I mentioned, I highly recommend that you make sure you know all the important dates for all your other classes and everything, start setting all that up. When it comes to the above and anything else related to the class, I do want to encourage you guys to actually use Piazza, the thing I set up a while back, kind of like a public forum. This is for a few reasons. So first of all, it's more efficient for me to respond so that I can actually answer a question and everyone can see the answer and I won't have to answer the same question for multiple people. But beyond that, it's actually better for you guys in several ways. So if you ask a question, if someone asks me a question in email, for example, and I answer the question in the email, it turns out a lot of times other students would benefit from that answer. And sometimes I would end up sharing the general answer anyway, but there are other times when I probably didn't think it's a big enough deal to share with everybody what I spoke about, the problem I solved in private. So there is something to be said about missing out on that, actually. So as you guys know, I'm taking my own classes this semester, trying to keep the rust off the brain, trying to keep the brain young. And I can tell you that there are times when seeing the questions that other people have can be beneficial, because then sometimes you don't even realize that there are questions that you didn't know to ask. Also, sometimes, occasionally, I also notice questions some people are asking. I'd be sitting in class and someone would ask a question, and on one level I'm like, well, isn't the answer to that obvious? But then the professor starts going into it and then he's talking about all these different angles and he's like, okay, well, usually this is obvious, but there's this one special case over here that you have to worry about. And I'm like, wow, I didn't know I had to look at it from that angle. So sometimes someone can ask a question, and even if you think you know what you're talking about, you think you're a big shot, you can learn a lot from the answer that can come from that, and some things that you have to look out for that you weren't aware of. So there are many unknowns in life. No one knows everything, but there are also things that are called unknown unknowns, which is like when you don't know something and you don't even know that you don't know it. So a public forum is actually a great way to uncover things like that. So that's another benefit to it. So someone else would ask a question, and based on the responses, you're going to realize, I never thought of it that way. Even if it's a topic that you're comfortable with, you can get even more comfortable. Second of all, or third of all at this point, you guys can answer each other's question, give your own inputs. I can, of course, endorse an answer, expand on an answer, and comment as well. And if you guys are shy, you can do this anonymously. But also, answering a question is also very useful. If any of you have tutored or anyone you know have tutored or taught before, they can tell you for sure one of the best ways to learn something is to actually teach it yourself. So you do actually benefit from answering questions and helping out your fellow students, because for you to get another mind outside your own to understand concept, you're usually going to have to break that concept down in your mind and probably explain it from an angle where you yourself never thought about it from that angle. And so you have to play around with a concept to get it in someone else's brain in such a way that now it makes you more used to the concept. It forces you to look at things from different angles, and you learn stuff by yourself, right? And again, the person you're teaching or asking a question might ask a question that you never thought of. Well, what about in this scenario? Could I still do that? And then you're going to realize, wow, I never thought of that. And then you kind of think about it, and now you can answer that. And you'd realize that you actually learn by teaching. So that's very good. Another thing is it would reinforce a sense of community, a sense of belonging. You're not just all out there on your own. You guys are all, you're in the same boat with other people. You're all working towards the same goal. So there are many reasons that I highly encourage you to take advantage of that, especially going into finals week. So you have any questions about the test? Do you have any questions about the final? Do you have any questions about math in general, some of the things you've been studying? I would highly encourage you to post it on Piazza. It would really be beneficial. And I don't really make suggestions unless I'm pretty sure they will work out. And I've been using some of these I've used these in the past, and I'm using these strategies in my current classes. And I'm telling you, they are helping. They've helped me. They've helped other people. So don't take that for granted. Yes.
So I'm gonna be in California, like when school closes. So am I gonna have to take the test at 5:30, like in the morning, on December 4th, like the second test?
That's something that you can talk to me about privately. Okay. So email me and let me know, and we'll figure that out. As soon as possible. So it's good that you're telling me way ahead of time. So something like that, when it has to deal with personal schedules, that you can email me personally and we'll fix it. Okay, so we'll figure something out. Let us see, what else can we do? Anything else I wanted to mention? Yeah, so fill out the doodle poll. That's when test 2, that's when the final is. Ask questions on Piazza, answer questions on Piazza. Yeah, so what I want to do now, again, kind of a community building kind of thing, but also to give you guys another resource that I think would be very useful and very helpful, is I want to put you guys in study groups. So I decided to split the class up manually, and I'm hoping you guys haven't been too bad with the participation. Most of my classes this semester are actually pretty bad at participating and engaging with the class. But hey, you can always engage more. And if you're ever, for those of you who are shy to engage with me or engage with the class, hopefully you are going to be feel comfortable enough to engage with your peers. At the very least, you should be able to do that. So I thought it was a good idea to put you guys into study groups so you guys can help each other out. Can be, that's going to be your clique in the class, your tribe. That's like, it's very hard to form those in an online setting. And for social reasons, as well as many other practical reasons, I think that would be a very good idea and very helpful. So I took the liberty of putting you guys into groups. And that is what I want us to start coordinating now. So I'm going to be creating some breakout rooms right now. Gonna have you guys go into a breakout room according to your group. I sent an email yesterday, last night, some point within the last 2 days. It was probably yesterday or the day before. Didn't get a lot of great sleep last night. I don't know what's up, so I might be a little bit off there by like a 24-hour period. But you all should know what group number you're in. So just in case you can't see the breakout rooms, you can tell me what group you're in and I can manually put you in there. So when I do put you into breakout rooms, there are two main goals that I want you guys to accomplish, and I'm going to give you guys 5-ish minutes to accomplish this. One, exchange contact information with everyone else in your group. So make sure everyone knows how to contact everyone else in that group. And two, designate a point person for that group, not a group leader or anything like that, but just someone to be the main liaison or the main contact with that group. So instead of talking to all the individuals in a group, I can just talk to that one person, and that person will disseminate the information among the group. Also, I think most people are here, but if anyone is absent in your group, then that designated person would email me and say, hey, this person was absent from our group, from our first group meeting, and I'll get them to contact you. So you want to make sure you have the contact information of everyone else, and designate someone to be the point person for the group that I can actually contact and know what's going on. And if you get that done within 5 minutes, then just sit around and chat for a little bit, get to know each other, do some team building, whatever. You guys can give yourselves a group name. We're Group 1, the Mighty Ducks, or we're Group 1, Student Alliance Against Jhevon's Tyranny, whatever. Just kind of bond, talk about each other, what you guys are doing, what other classes you're taking. You might notice that other people in your group are doing the same courses you are, and you might be able to study on more than one account and build some good relationship and a network that will help you out. So that is what we're going to do right now. And let me initiate that. So I don't know if in your other classes you guys have used the breakout room feature, but I just opened all the rooms. You should be able to see it and go into it. And it seems like some people are moving in there already. Most people see it. Okay. If you can't see the breakout room, let me know.
I can't see it.
Okay. Who's that? Oh, wait. Don't tell me yet. Don't tell me yet. If we're going to be doing names, I want to maintain your privacy. So let me stop recording. And then when we come back for the main part of class, someone remind me to start recording again. Okay, we're back. Okay, everything's being recorded. Everything looks okay. All right, so great. Looks like you guys are getting along. That is good. And it also seemed just by chance, like one of the groups mentioned to me that they already knew each other and they were good friends. I don't know. That was not intentional. It would be cool if you got to meet someone new. But yeah, I don't know. I guess a lot of you, if you're in this class, chances are you're all kind of in the sciences or kind of on the same track for the most part. So I guess it would have happened eventually. But yeah, hopefully being in groups is going to help you guys out moving forward. And yeah, so at the moment, since we already spent a lot of time, let's actually just jump back into the material. So quick recap. Last time we introduced the idea of a polar coordinates or the polar coordinate system, and it was just a different way to locate points in our space. So we are all used to the rectangular coordinate system. I give you an x, y coordinate. X tells you how much you move horizontal, y tells you how much you move vertical, and basically through constructions of rectangles, you can identify locations. Polar coordinate system uses circles and angles, and essentially now the location identifying characteristics are a distance from the origin and an angle that you make with the positive x-axis. So that's basically it. So we just changed the way that we're measuring location, and it turns out that actually is pretty useful. So by thinking of location in this way and thinking of the points in the plane as being identified in terms of the variables r and theta, you say you're working in a polar coordinate system. Okay. as opposed to everything you've been doing up to now. You've been doing in what's called the rectangular coordinate system or the Cartesian system, or people might also call it the Euclidean system. When you get to multi-1, you're going to learn about another kind of coordinate system called the spherical coordinate system, which is very useful in some instances, particularly to physicists and engineers, I guess, but a lot of engineers would use the spherical coordinate system as well. But we are talking about the polar coordinate system. In higher dimensions, this might be referred to as the cylindrical coordinate system. Okay, so that's pretty much all we did here. So yeah, then we got to the announcements. So we're picking up here. Okay, so let's actually practice finding locations in this coordinate system. So if you wanted to locate a point 1 comma pi over 4, which I'm thinking of this as r comma theta. Remember, r is going to be our distance from the origin, and the theta is going to be the angle that we make with the positive x-axis. So pretty much I would think of this as boom, boom, boom. I can move an angle of pi over 4. And if I extend a distance from the origin of length 1, this coordinate that I would hit is actually going to be the coordinate 1 comma pi over 4. So its location is in the first quadrant. And yeah, that's basically it. That's the point. Now, one thing I want you to notice here is because our theta represents angles, we also know that you can have different angles that terminate at the same location or the same point. These guys are called coterminal angles. So that's something you would have learned about in pre-calc. So that basically tells you that there are other ways to look at this point. So this is the same as, for example, I could have gone and added a 2 pi and go all the way around here and come back here and then extend. And I would actually hit the same point by adding a 2 pi. So here, this is also equivalent to the point 1 comma pi over 4 plus 2 pi, which is 9 pi over 4. Right? So if I take pi over 4 and I add to it 8 pi over 4, which is 2 pi, it's essentially the same angle. So what you'll notice from this is polar coordinate locations are not unique. In fact, there's an infinite number of ways you can describe any given location. It's worth mentioning that this is not true in the rectangular coordinate system. The coordinate 1 comma 5, there's no other address for that coordinate. However, in the polar coordinate system, you can have multiple addresses for the same location based on how you're measuring angles. You can also change location based on how the address of your location, based on how you measure the R as well. And I do want to talk about that. So it's possible you might think of the R, because I mentioned it as the distance from the origin, you might have the idea that the R cannot be negative. However, this is not the case. We do allow negative values for R. Now, how do we interpret these negative values is important. In general, and this is true even with the rectangular coordinate system, we interpret negatives as a change in direction, right? So if the x-coordinate is positive, we move to the right. The x-coordinate is negative, we move to the left. The y-coordinate is positive, we move up. If the y-coordinate is negative, we move down. The same kind of idea applies here. So whether our theta or our r value is negative, it basically means a change in direction. So what would a negative r look like? So for example, this coordinate, if I wanted to plot the point r comma theta equals -1 comma pi over 4, what would that look like? Well, again, we can think of me measuring the angle pi over 4 because that's my theta. No qualms there. And so what we would realize is that if I were to extend by 1 unit away in that direction, then this would be actually 1 comma pi over 4. However, how do I interpret the fact that there's a -1 is you literally go in the opposite direction. So what the negative r value means is instead of going towards the angle pi over 4, you're actually going to go back. So this is your coordinate -1 comma pi over 4. You literally flip the direction the opposite. So just like how in rectangular coordinates, instead of going right, you go left, you literally turn around 180 degrees and go in the opposite way, right? And so that's how we interpret negative directions. And again, you can mix and match this with angles, with various angles. So there are multiple ways I can get to that point. So something I can note, I want to put this in a different color. Note. So even something like -1 comma pi over 4, notice that that would be the same as me saying something like 1 comma 5 pi over 4 by just adding pi or any odd multiple of pi. And I could do, that's the same as 1 comma 9 pi over 4. It's also the same as, say, -1, and I can add 2 pi to this. And so on, right? So I can have multiple addresses, an infinite number of addresses by either I can add 2 pi to this coordinate here, to the theta for that coordinate, add or subtract multiples of 2 pi, or I can add or subtract multiples of pi to this coordinate, or odd multiples of pi. So this guy shouldn't actually be there because I want to make sure that I flip it, okay? So again, multiple ways to write down the same point. So that's the difference between, that's one of the major differences between polar coordinates and rectangular coordinates. But as long as everyone kind of agrees that, okay, every time we're going to give a location, we're only going to assume our angle is somewhere between 0 and 2 pi, then everyone can be on the same page and not worry about it. But you do have to be aware that there are multiple ways to talk about the same thing. When it comes to, yeah, as I was mentioning here, that's what I was mentioning here. That's what I was mentioning here. And do I want to say anything else there? I left some space, but yeah, maybe I can do some more examples. So for example, we already saw here that blue. So let's say I do 1 comma pi over 4. That leads me here. Call that the blue one. I could also do 9 pi over 4, let's say with a green. That would bring me all the way around here, and I'd still extend to be the same thing. Or I could do something like do a -1 with a 5 pi over 4. So what I would do is go 5 pi over 4, which would bring me down here, and then I flip in the negative to go back to the original. So tons of ways to get to the same point. In terms of I'm not really going to do any examples with theta being negative because theta being negative is interpreted the same way that you did way back when. You can think of theta literally in exactly the same way you've always thought of theta. So whenever theta is positive, you measure the angle going counterclockwise from the positive x-axis. When theta is negative, you measure your angle going clockwise from the positive x-axis. So something like, say, example. If I have -1 comma minus pi over 4, and I just literally just made that up, how I would actually do that is, of course, first I measure the minus pi over 4, which is actually pi over 4 in this way. And I know 1 would be directing in that position, which means our -1 is going to be directed in the opposite position. So this is going to be that coordinate. Okay. Any questions on anything I said so far? Okay, so I'm going to assume we're all good. Moving on. Now, of course, with all this in mind, obviously, trigonometry is our friend here. So you need to remember your trig, not only for this, but for all sorts of reasons. Of course, you would notice that if I were to actually start sketching things out here, and I have some sort of point here where this has length r and that has theta, then obviously this here would create a right triangle. And so my height here is going to be, well, it's the opposite. So it's actually going to be r sine theta, which is actually the height. So that is the y coordinate, right? Because that literally measures the height you move over here. Also, if I went along the length, the base here, that is the adjacent side. So of course that is r cosine theta, and that is the x coordinate, right? Because that measures up to this point here. So as a result, you can think of your x as r cosine theta and your y as r sine theta. You can also notice that this is pretty much like thinking of a circle with center 0, 0 from our parametric equations. So you can also think of polar coordinates as, yeah, you're setting up a new way to locate things in your universe based on a set of parametric equations. If I force my x to behave like an x r cosine theta, and I force my y to behave like an r sine theta, then polar coordinates is how my universe would now locate things. And of course, if I wanted to do this, well, that would be the equation of the circle centered at the origin with radius r. So that's going to be true. And of course, if I want to solve for theta, I can just do, well, tangent of theta is opposite over adjacent. And so I can find the opposite side is the y, the adjacent side is the x. So I can find my theta by tangent inverse of y over x. If for some reason the tangent inverse is not defined, say like your x would give you 0 or something like that, you can also use the other ones, just to be clear. So I could also use the fact of something like theta, I can think of it as cosine inverse of x over r. I could also think of it as the sine inverse of y over r, etc. So trig works. So if you remember all your trig identities, that can be useful. These guys are very useful because this set of equations here, it's useful in converting. So if, and again, a lot of times when you have two different systems to do something, you might be interested in converting from one system to the other. So the first pair of equations are very useful in converting from a polar coordinate system back to a rectangular coordinate system. And the second pair of equations is very useful to convert from a rectangular coordinate system to a polar coordinate system. So if I gave you xy and you need to find r theta, you can use the second pair of equations. If I gave an r theta and you need to find x and y, you can use the first pair of equations. That's going to be important on multiple levels. But for now, what we're from one coordinate system to another on a point-by-point basis. So that leads us to this example. So now, we're going to change two coordinates. So I gave you two polar coordinates here. R comma theta equals 2 comma pi, and r comma theta equals radical 3 comma pi over 6. And I want you to change both of these to rectangular coordinates. So let's do the first one. Okay. So here I'm given r comma theta, and I want to switch to x comma y. So what do? Well, I would notice that x is equal to r cosine theta. That's going to be 2 cosine pi. Cosine of pi is -1, so that's -2. My y is r sine. This is sine of pi. So this means my xy coordinate is -2 comma 0. And that actually makes a lot of sense. Because if I were to do an angle pi, that would be this angle here. And then I would extend from that a distance of 2. So the coordinate I would obtain is, of course, going to be -2 comma 0 in the rectangular coordinate system. And now I've located that point. Questions on that? Okay, I think we're okay. Yeah. Imagine we went from like integration by partial fractions to this. Yeah, don't worry. It'll get a little bit more interesting as we go on. It's not going to get harder, not as hard as the previous topics, but we'll get to some more interesting stuff soon. Yeah, let's just do the other one. Was that it? Radical 3 pi over 6. Again, same plug and chug. If you know those formulas, which I'd highly recommend you memorize, by the way. I know technically you're doing things online, but there is something to be said about memorization. You should memorize this. I know a lot of there are a lot of people, especially recently, they're kind of the opinion, well, we shouldn't teach math by memorizing and rote memorization and blah 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 and da da da. We should teach students how to derive and blah blah blah. If I may say with all courtesy, those people don't know what they're talking about. You need a bit of both. At the end of the day, you have to memorize something. You have to have some knowledge in your head to be good at manipulating that knowledge. So yeah, if you have nothing memorized, you are not going to be very efficient and you're not going to be very masterful anyway. So there are some things you want to memorize. Sure, I would jump on the bandwagon that says you should teach students to memorize the least amount of things as possible and still be effective. Sure, I would agree with that. But there are some things that you need to memorize. And I would memorize these guys. So again, x equals r cosine theta. It's like here, you should memorize what cosine of pi over 6 is. So this is radical 3. What's cosine of pi over 6?
Square root 3 over 2.
Right, root 3 over 2. So that's 3 over 2. Y is our sine theta. This is radical 3 sine of pi over 6. Sine of pi over 6 is a half. So this is radical 3 over 2. So this would mean the xy coordinate is 3 over 2 comma radical 3 over 2. Did I box my answer last time? Okay. And does that actually make sense? Well, let's see. I moved pi over 6, so that's like 30 degrees here. And then I extended by radical 3 length. And so I would have a coordinate here. Does it make sense that that coordinate could be like a 3 over 2 and a radical 3 over 2? Yeah, I'd be convinced of that. Both my x and y coordinates are positive. So yeah, being in the first quadrant makes sense. So I'm satisfied with that. Let me stay here for a little while. Hopefully you guys don't have any questions. You can copy that. Okay, we're going to do the opposite. So normally when someone just mentions coordinates, you can kind of assume they're talking about XY coordinates because it is the thing that most people at this point will be used to. So they're usually not going to identify that they're talking about XY coordinates. At this point, if I do want to talk about polar coordinates, I will specifically mention r theta equals something here. Okay. But if someone just listed coordinates here, you can pretty much assume that they're talking about rectangular, unless they indicate somewhere else, indicated otherwise somewhere else. So I have the point 1 comma 1. I know where that should be, right? So that's just a point here. Right, so we all know how to find that pretty easily. Now let's actually convert to polar coordinates. So here is where we're going to do use the other pair of equations. So we know that x squared plus y squared is equal to r squared. So this means that 2 must be equal to r squared. So of course my r is going to be plus or minus radical 2. And so already now we have some ambiguity. We have a sign ambiguity here. We'll come back to dealing with that later. Also, now as well, what I can do is I know that theta is equal to tan inverse of y over x, which means that's tan inverse of 1. So that's pi over 4. Of course, it can be plus 2 k pi. Or in fact, it could be plus k pi. So what I would say is, let's say you want to ignore this part. So you would take theta equals pi over 4. That will also tell you what you, that will help you choose your r value. So picking an angle helps you choose your r value. Because remember, there's an infinite number of ways I can describe this angle. However, I'm going to just pick one arbitrarily. It's usually nice to pick one between 0 and 2 pi. the smallest positive one between 0 and 2 pi. So picking an angle helps you choose an r. So here, now that I know that I do want to move a positive pi over 4, it makes sense that if going this way would be a positive r would move in this direction, and a negative r would move in this direction. So clearly, if I want to keep the angle pi over 4, the positive r is the one I want to pick. This makes sense here. So this is the coordinate I want. It makes sense because it's in the first quadrant, just like I know it should be based on the rectangular address. And so that's the coordinate. That would be the coordinate positive radical 2, comma pi over 4. So I could say my r comma theta would be positive radical 2, comma pi over 4. And usually that would be good enough. Of course, there are some times when the question might be asked, write down all possible polar coordinate addresses or something like that. So I can embellish on this a little bit. If asked, find all possible polar coordinate representatives. Then, of course, I know I could keep the radical 2 and then just keep doing the coterminal angles. So I would just say it's pi over 4 plus 2 n pi, where n is any integer. And now I do a set of points where someone could have picked the negative r if they wanted, in which case I know I need to first add pi to the original angle, which would give me 5 pi over 4. And then I add all other multiples. And this would be my answer in that case. Okay. So just realize that if I give you an r comma theta, you can always add any multiple of 2 pi to the theta. It's not going to make a difference. And if I give you r comma theta, what you can do is you can take the negative r got startled. My headphones are still connected to my phone. I think someone's trying to call me. It's like totally. So if I make the r negative, then I can just add pi to the angle and then repeat every 2 pi after that. Right. So I think I typed that all out in an earlier example. But yeah, hopefully that's okay. Let's see 0, 2. Okay, so here I know my x is equal to, I know my xy is equal to 0, 2. So in rectangular coordinates, I know how to plot this very well. So my x is 0, y is 2. It's up here. Yeah. And so now, pretty much when you're used to this, you'll be able to read off the answer right off the bat. Notice here that that's just pi over 2. And then the distance here is 2. So we already know, you can look at this and know that 2 comma pi over 2 is going to be one of the answers, right? So you can actually look at, sometimes the picture, again, it's going to be obvious what it is. So here, what I can do is, again, if I want to go by the equations, x squared plus y squared equals r squared. This means that if I plug in x equals 0, y equals 2, then my r would be plus or minus 2. And then I can have, notice that here, if I use my theta equals tan inverse of y over x, notice that this would be undefined. Now, from being undefined, you can conclude that your theta is going to be some odd multiple of pi over 2. But if that's still kind of worded out for you, well, you could instead use just one of the other ones. So we also know that theta, we can also write that as cosine inverse of x over r. But if my x is 0, that gives me cosine inverse of 0. So that also gives me pi over 2 plus 2k pi or minus pi over 2 plus k pi. Or something like that, right? So that leads us to, I can think of my r comma theta as, of course, pi over 2, stretching 2 units up. And so this coordinate is going to be r comma theta equals 2 comma pi over 2. All of them, I can do something like 2 comma pi over 2 plus 2n pi. That would just keep revolving around on itself. Or I can do minus 2, in which case it would be the opposite. And then I could do something like 3 pi over 2 plus 2n pi, where n equals any integer. And that could be the answer. So if you only care about one point, you can write it in any of those variants. Any questions on this one? So converting from rectangular to polar is a little bit more nuanced, but are we good so far?
Yes.
Okay. All right, moving on. So something that's going to be very convenient, especially moving into the next class, into Multi-1, is being able to describe regions in terms of polar coordinates. So hopefully you know how to do this in terms of rectangular coordinates already. And I'll also write down the rectangular coordinates ways of describing these regions as well. But being able to describe a region in polar coordinates is going to be very, very useful. for when you do like double integrals in cylindrical coordinates in the next class. So I want you guys to know how to actually describe a region in polar coordinates. So for example, we can just jump into it actually. Describe in polar coordinates the region in the plane bounded by the quarter circle in the first quadrant, blah, and the positive axes. So here, I'm asking you, well, if I, draw a circle of radius 3, and I want to bound it in, I want the quarter circle in the first quadrant. So this is a boundary, and the positive axes. So this is another boundary, and this is another boundary. So I'm talking about this region right here, this little pizza slice looking thing. So now the question is, how would I describe that region in polar coordinates? So basically, I have to say what my r is doing and what my theta is doing. And I have to somehow describe these guys in inequalities. So we know that when we want to describe a shaded region in space, we usually use inequalities because we're not just want to be at a point, but we want to be either at every point beyond that or every point before that. So doing it in terms of inequalities would be how you'd want to describe it. So what do you guys think? How would I describe this region?
Wouldn't R be 3 for everything in that quarter circle?
No. So r equals 3 means your distance is 3 units from the origin, right? So if I say r equals 3, that is literally just the edge of the circle, right? Because that's where the distance is 3.
So r is greater than or equal to 0 and less than or equal to 3.
Right. It has to be between 0 and 3, right? Because I want the entire shaded region. Notice that if I were to pick a point like inside the shaded region, its distance from the origin will be less than 3. It'll be somewhere between 0 and 3, right? So I don't only want the outer edge. The outer edge is where r equals 3. But if I want everything in between that, I have to measure everything from the origin all the way out. So it's actually 0 to 3. And yeah, Hannah got it in the chat as well. Right? What about theta?
Greater than 0, less than pi over 2.
Yeah, somewhere greater than or including 0, less than pi over 2, which is 90 degrees. This is how I would describe this region. Now, there are a couple things. So that's literally the answer. Okay, so nothing really to calculate here. It's just kind of something you should know. Now, there are a couple things I do want to bring to your attention here. So being able to describe that is already going to let your, this already will simplify a lot of calculations. And I would say, to kind of convince you of that, we can compare to the rectangular coordinates, which I'm going to write down in a bit. But also, something else I want you to notice, which is going to, hopefully you'll be able to get some appreciation for why in calculus this might be useful. This is also useful because in the r theta universe, this region describes a, what do you think? If I were to draw a pair of axes, but let's say I'm not in the XY universe, I'm now in the r theta universe. So let's say I put r on the vertical axis and I put theta on the horizontal axis. What kind of shape am I describing here? So if it makes it any easier, you could even replace r with y and replace x with theta with x. So if you saw x is between 0 and 3 and your y is between 0 and pi over 2, and you were to sketch that region, what would that region look like?
You hear me?
I couldn't hear you.
Can you hear me now?
Yes.
All right, it'll be a rectangle.
It would be a rectangle. So notice here, if I just allow my theta to be anything between 0 and pi over 2, and I allow my r to be anything between 0 and 3, this literally creates a rectangle. Now, rectangles should be something near and dear to your heart. You guys developed the integral based on rectangles. It might be useful when it comes to integration, you might think. In terms of the region, this region is more complicated when considering integrals than this region, right? So that's going to be useful for calculus. And I'll let your multi-one teacher explore that with you. A lot of times rectangular regions are more easier. So if I have this weird region and I can just convert it to another situation where I have a rectangular region, a lot of times for calculus, especially like integrations where I want to set up a Riemann sum, that's a pretty useful thing to be able to do. Now, as well as it's actually simpler even on a direct computational level in this case. Notice here, if I were to describe in rectangular, note, description in rectangular. Then again, I'm using this guy here. How would I actually describe that in rectangular? There are probably several ways, but here's one way. I could describe this by saying it's the set of all xy such that this is 3. I can say my x goes between 0 and 3, which doesn't look so bad. But how would I describe my y? What do you guys think? Describe y.
Greater than 0, but less than something quadratic.
Not even quadratic, but almost. So what were the original equations? Well, we were told that this was the circle, right? X squared plus y squared equals 9.
So square root.
right? You need the square root of 9 minus x squared, right? Now, especially after trig sub, an expression like that should like give you cold sweats and nightmares. I mean, look at this description of the region and compare it to this description of the region. The polar coordinates description, I only need constants to describe this region. Whereas in the rectangular coordinates description, I literally need a radical function, with a quadratic in it, right? So even on a purely computational basis, like I'd rather work with a pi over 2 than with a square root of 9 minus x squared for most calculations. Come on, right? If I had the choice to choose between constants, working with constants versus working with a radical function, it's a no-brainer. Give me the constants, right? So you can already see that when it comes to like a circular region, the polar coordinates actually gives you simpler descriptions at the end of the day. So how many things to it? So I will keep you guys a few more minutes, but I will 5 of those minutes, I want you guys to I don't know. Maybe I think work together. Let's do group 1, 2, 3, 4, 5. Okay, let's do that. I just went down and back up. So what I want you guys to do, write this down and or take a picture or a screenshot or whatever. I'm gonna put you guys in your breakout rooms again, and I'll pull you back after 5 minutes, and you guys tell me what the answer is. So let's actually try that. Boom. Okay, so I'm asking some questions in the chat. Please respond in the chat.
I don't think I got put in a group.
I'm pretty sure everyone did, but I sent an email last night. Hold on.
Oh no, I didn't get like the breakout room thing.
Okay, yeah, so just type your group in the chat. And we're back. Okay, all right. So volunteer from group 1 or 5, tell me about what's your answer to the first one.
So for R, we said that R is greater than or equal to 1 and less than or equal to 3.
Okay.
And then for theta, we said greater than 0 and less than or equal to, well, greater than or equal to 0 and then less than or equal to 2 pi.
Okay, so that's what we believe is the answer. Does that actually make sense? Well, let's see. What is the picture here? Right. So we have two regions, x squared plus y squared less than or equal to 9. So that's like a circle of radius. Circle of radius 3. And we want to be less than that. So we want to be everything inside of this circle. And we also have a circle, x squared plus y squared equals 1 is actually a circle of radius 1. And we want to be everything outside of that circle. So obviously we need to achieve both at the same time. So we really want the double shaded region. And so, yeah, it's this. Right, so that's like a washer, kind of like a CD-ROM disk or whatever. So that's called an annulus is the correct name for that. And of course, as you could see, it makes sense that your R goes from 1. So this is where R equals 1. And out here is where R equals 3. So R going from 1 to 3 makes a lot of sense. Also, because all quadrants are accounted for, theta goes from 0 to 2 pi makes a lot of sense. So notice here, whereas yeah, so that is correct. What I can do is for comparison, what would that look like in rectangular coordinates? Well, I want to be inside the circle of radius 3, so it would be something like my y value has to be less than or equal to the radical of 9 minus x squared, but greater than or equal to the to minus 9 minus x squared. At the same time, I want my y to be also y must be greater than or equal to the radical of 1 minus x squared. And I actually want it to be less than or equal to negative radical 1 minus x squared. And then I want to say my x range is going to be something like minus 3 to 3. Anyway, it's as you can see, it's going to be very complicated. And I probably need to split these guys up into 2 parts. Because that's kind of weird to be bigger than a positive number, but smaller than a negative split. Yeah, so that's just to give you an idea. Can't let me write those two out. So I would need my y to be bigger than or equal to 1 minus x squared. At the same time, I would want it to be less than or equal to minus 1 minus x squared. I need like all of these. And I would need like my x to be in, well, between -1 and 1. And or some complicated mess. As you can see, it's like, it's really annoying to even describe this guy in rectangular coordinates. I mean, yeah, I can describe it in words as I did here, but at the same time, if you want to like set things up as a bunch of equations that you're going to be working with, that's hella annoying, right? So someone from group 2 or group 4, tell me the answer that you got.
I volunteer. Okay, so
Sure.
my group didn't understand the question at first, myself included. But after looking at the previous question, I finally get it. So 0 is less than or equal to r, which is less than or equal to 1. And the angles are negative pi over 4 is less than or equal to theta, which is less than or equal to 5 pi over 4. And the cross section of it looks like a pizza. You sliced it diagonally, but you took the bottom slice away.
Okay, yeah, so you're talking about the picture.
Yeah.
Okay, so let's actually look at the picture. Okay, that's probably nicer. Okay, so y greater than or equal to x. So you have the line y equals x. That should go through the origin. Y equals x. But you want y to be greater than or equal to x. So you want to be above this line. You have y equals minus x. So y equals minus x. And you want your y to be greater than. So you also want to be above that line. Then you have the circle x squared plus y squared equals 1. So then that just gives you a circle here of radius 1. But now you want to be less than. So you want to be inside that circle. But at the same, so you want to be above these two straight lines, but at the same time, you want to be above the lines at the same time, but inside the circle. That's this region right here. Right? I can't be over here because I would be above the y equals x line, but I would be below the minus x line. So that doesn't work. Can be over here because I'd be above the minus x line, but below the y equals x line. So that's not going to work. Can be over here. I'm below both of them. Same thing for over here. So that's the part that we care about. Right? Want to revise your answer?
Okay, yeah. So the angles are pi over 4 is less than or equal to theta, which is less than or equal to 3 pi over 4.
Right. Sometimes drawing a picture is going to be very useful. And that's a pro tip for Calculus 3, for Multi 1, as they would call it. So there are a lot of times students are very afraid to draw pictures. Draw a picture. It can actually clear up a lot of things for you. So I don't know how far we'll get with sketching in this class, but for Calculus 3, the way to do it like a boss is to be able to sketch in 3D. That's going to be very useful.
I have a question.
Yes.
Why does this not include that same shape, but like mirrored over the x-axis, the lower part?
Which part? Like right here?
No, sorry, the one in the like the lower middle triangles.
Here?
No, two more over. Like the mirror
here?
image of that. No, the mirror image of the shaded area.
Oh, like here?
Yeah, thank you.
Okay. If I ask you, can I be over here? The answer is no, because that would mean my y is less than minus x.
Oh, okay.
Right? I need my y to be above this line at all times. Yeah, I need to be
Okay.
above both of the straight lines at all times. Yeah, and I mean, the description given here would actually work. So I could, you know, and something like y less than so something like that could be a rectangular coordinates description, and you might want to tell them what your x values will be. But yeah, this one, of course, we'll pick up with this later. Of course, you guys can try this for next class, but we'll finish with this last example here. Someone in group 3?
I'll volunteer.
Okay.
So we had that our radius is going to be greater than or equal to 0 and less than or equal to 4, and that theta will be greater than or equal to 0 but less than or equal to 2 pi.
Right. So this one is actually not so bad. It's just all the guys inside the circle of radius 4. And so, yeah. In rectangular, could say something like y needs to be less than 16 minus x squared, but greater than 4 minus x squared. And my x is going to be between minus 4 and 4. Right, so just for comparison, and as you can see, in all of these cases where we have parts of a circle or segments of a circle, polar coordinates is a much simpler description. I can describe all of them essentially as easily as I can describe a rectangle in polar coordinates. So yeah, we went over time, but that was because you guys had to get into your groups. So I will let you guys go. Thank you for your attention. Thank you for hanging out, and we'll stop there. I'll see you guys again tomorrow. Remember, so you don't have a quiz tomorrow, we'll have another class. So I'll see you guys bright and early at 8:30 tomorrow. Until then, have a good rest. Good luck for the rest of the semester, and I will see you guys in the next one.